Hello there, and welcome to Origins of Earth, where curiosity gets cozy and science drifts gently like a tide.
Tonight, we're going far back in time, to a world before forests, before insects,
Before anything had ever taken a step onto dry land. The Earth then was almost entirely blue. Waves stretched from horizon to horizon, and beneath them, the first great civilizations of life were quietly taking shape.
This is the story of when life came out of the ocean.
A story that begins in darkness, in salt water, and in silence.
It's a tale older than any mountain, older even than the continents as we know them.
Wherever you're listening from tonight, perhaps you can imagine that distant ocean. The air around you, the breath you take in and let out, all of it has been part of this planet's endless circulation of water. Once upon a time, every drop passed through those ancient seas, washing over creatures that look nothing like anything alive today. Strange, soft-bodied creatures like sea slugs drifted with the current, and tiny plankton shimmered like galaxies in suspension. The world was quieter then. There was no bird song, no rustling of trees, no chirp or croak or cry. Just the hiss of tides and the hum of a newborn biosphere learning to breathe. Before we dive beneath that surface, I'd love to know where you're listening from. Maybe you're somewhere near the ocean yourself, or perhaps far inland, where the nearest waves are locked in stone.
Either way, you're still connected to that ancient sea. If you find this kind of quiet science soothing, if you enjoy letting your mind drift through deep time, I'd be ever so grateful if you'd like the video or subscribe. It helps this small corner of calm reach others who might need a gentle voyage through history tonight. Now, let's take a slow breath together.
Imagine the world nearly 500 million years ago, the Ordovician period.
The second chapter of the Paleozoic era, following the chaotic creativity of the Cambrian explosion. Life was still almost entirely aquatic, but it had found its rhythm. The oceans had become both nursery and battleground. They shimmered with horseshoe crab trilobites crawling across sandy bottoms, with floating moon jelly creatures drifting in the light, and with coral colonies starting to piece together the first real reefs in Earth's history. The land, meanwhile, lay barren and silent, nothing but rock and wind. The color green had not yet reached the continents. In these ancient seas, sunlight reached only so far.
The top layers, called the phototic zone, were bathed in light and alive with photosynthesis. Microscopic algae and cyanobacteria captured sunlight and turned it into energy,
releasing oxygen that would slowly, over millions of years, change the atmosphere itself.
Below that bright layer, darkness returned, cold and still, inhabited by strange forms that glowed faintly, or sensed vibrations instead of sight.
The water carried minerals from young, restless continents, feeding plankton blooms that colored the shallows. If you could stand on the seafloor, then you wouldn't recognize it as the same planet.
There were no fish yet, no bones, no true plants, but there were hints of what would come. Tiny shelled creatures, some no bigger than grains of sand, were becoming more common.
They secreted calcium carbonate, slowly learning to build protection around their fragile bodies. Others developed primitive jaws or tentacles, small innovations that would ripple through evolution for millions of years.
The Ordovician was an age of experimentation, a long and steady refining of what life could be. And above all, there was movement. Continents were not where they are now.
The world's land masses were scattered across the southern hemisphere, slowly drifting like rafts on a vast sea of molten rock.
What would one day be North America was then a tropical island continent called Laurentia.
Surrounded by warm, shallow seas rich with coral and cryoids. The aerial shot dips below the water's surface.
To the south, the immense landmass of Gondwana stretched toward the pole.
Wrapped in glaciers and cold winds that hinted at the ice age to come.
The Earth's climate was capricious, warm and tropical near the equator, but cooling over time as carbon dioxide. In those seas, life was becoming more intricate. Animals that had once simply floated began to crawl, burrow, and grasp.
Predator and prey were learning to outthink each other in slow motion.
The first great food webs formed, a cascade of dependence that linked tiny plankton to larger swimmers. Then to the towering cephalopods, the nautiloids, rulers of the Ordovician seas. The food web visualization.
Imagine long conical shells as tall as a human, drifting like spears through the water.
Their tentacles coiling out to catch prey. They were the first true ocean hunters.
The prototypes for squids and octopuses yet to come.
The reefs beneath them were bustling microcosms, full of brittle stars, various brachiopod species, and fan corals. Some corals were solitary, others colonial, slowly growing into structures that would one day harden into limestone cliffs.
Over countless generations, their skeletons piled upon each other, turning living reefs into fossilized memory.
If you could hold a piece of Ordovician limestone in your hand today,
you'd be holding millions of lives compressed into a single stone, each grain a whisper from that ancient sea.
at the same time, the atmosphere above was changing in ways no one could yet notice.
Photosynthetic microbes in the ocean had been releasing oxygen for hundreds of millions of years. But now the balance began to tip. The air was still thin compared to today. But for the first time, oxygen levels reached a point that was...
The ocean itself was becoming layered. Shallow zones rich in oxygen, deeper zones poor in it. Creatures evolved to fill each niche, some thriving in light, and others hiding in the dark. Yet, while life multiplied in the ocean, the land waited. The coastline was still bare. Simple algae and microbial mats started to spread over damp rocks, clinging to surfaces just above the tide. They formed thin green films that shimmered in the light, quietly testing what it might mean to exist between sea and sky.
These were the first pioneers of land, though they didn't know it.
Over time, they would pave the way for mosses, then ferns, and eventually forests.
But for now, the land was only a frontier of moisture and rock. The Ordovician lasted around 41 million years,
a long, unhurried interval in the story of Earth. During that time, the number of marine species tripled. Ecosystems became more layered, more complex, and more stable. This diversification laid the groundwork for all future evolution.
The reefs provided shelter, the open ocean provided space, and the continents provided new sources of minerals and nutrients. As weathering broke down rocks into clay and silt, rivers carried that material to the sea, enriching it and fueling more growth.
It was a planetary feedback loop of chemistry and life, the ocean feeding on the land and life feeding on the ocean.
But not everything was peaceful. The Ordovician seas could be violent too.
Storms swept across the shallow continental shelves, stirring up sediment and reshaping coastlines.
Volcanic eruptions darkened the skies and poisoned the water with metal-rich ash.
Mass blooms of plankton could turn seas opaque, starving deeper layers of oxygen and causing die-offs. These were natural cycles of creation and collapse. Long before humans, long before anything with lungs or leaves,
The planet was learning balance the hard way. And in that push and pull, something miraculous was happening. Complex ecosystems, true communities of life, were beginning to form.
Coral reefs were not just structures, but neighborhoods with different species coexisting in precise relationships.
tiny bloodworms burrowed through the sand, recycling nutrients. Crinoids stretched their feathery arms to catch drifting food.
Trilobites scuttled across the bottom, leaving tracks that would fossilize into records of their daily lives.
Every niche, every surface, every current held opportunity. Over time, these systems became more resilient. They could recover from disturbances faster. When one species declined, another often filled its role. This resilience would be tested later when the first great extinction struck. But for now, the oceans thrived.
The Ordovician was a period of abundance, of refinement, of life taking its first confident breaths. And through it all, the continents continue their slow drift, unhurried and unstoppable. Mountains rose, weathered, and dissolved. Sea levels rose and fell.
The chemistry of the oceans changed subtly, steering evolution in invisible ways.
Calcium carbonate became the currency of survival as shells and skeletons became common tools. In a sense, this was the dawn of architecture, the beginning of organisms shaping not just themselves, but their environment. Reefs grew taller, sediments thickest, coastlines hardened. The planet itself began to record life's progress in stone. If you were to float above those waters, watching the slow ballet of early animals, it would feel both alien and oddly familiar. The rules were the same ones that guide ecosystems today: competition, cooperation, adaptation, and chance.
Only the players were different. And while it might have looked still from a distance, change was everywhere.
Evolution never stopped adjusting, improving, and reimagining the living world.
Somewhere in those shallow seas, a tiny organism, a planktonic copepod, found itself drawn toward the edge of the tide. Perhaps it was carried by a current, or trapped in a shrinking pool, or simply clinging to damp rock.
It might have been a mat of algae, or a simple worm-like creature struggling against desiccation and sunlight.
For a brief moment, it experienced something new. The boundary between water and air. That moment, multiplied over millions of years, would become the first step toward everything that would one day crawl, walk, or fly. So as we drift deeper into this story, picture the order of vision not as a static tableau, but as a living pulse. Oceans breathing, continents stirring, and life learning. A planet halfway between chaos and order, where every ripple carried potential. The surface glittered with sunlight.
The depths whispered with unseen movement, and somewhere in between, the ancestors of all terrestrial life were rehearsing their first steps. Now the water grows clearer, the sunlight deepens, and our journey continues toward the first great
A time when the oceans became not just a cradle, but a cathedral of life. The ocean of the Ordovician world was not one single blue expanse, but a patchwork of stillness and turbulence.
There were places where the water moved so gently that layers of silt could rest undisturbed for centuries.
And others, where storms churned the sea with a violence that scattered coral and shattered shells. Between these extremes, life learned to adapt, balancing fragility with resilience, learning how to endure both calm and chaos.
To exist in the Orvish Ocean was to live in a rhythm older than music, driven by currents, temperature.
If you could have hovered above one of those ancient seas, you might have seen something that looked almost familiar at first.
Below the seabed was patterned with ripples of sand, sculpted by gentle waves and cross-currents.
But the closer you looked, the stranger it became. The shapes of the living things below were unlike anything swimming today.
Trilobites moved like armored carpets, dozens of legs working in perfect coordination as they sifted the sediment for food.
Coelaes anchored themselves to rocks, stretching feathery arms upward to catch drifting particles.
Worms traced invisible paths through the sand, leaving winding trails that would one day become fossils.
The stillness was deceptive. Even in calm water, countless small events were unfolding at every moment. Microbes divided, shells grew, bits of organic matter settled to the bottom and were buried. The seabed was a slow conveyor belt of time, recording each pulse of life in thin layers of mud.
When those layers hardened into stone, they would preserve the outlines of shells and bodies in astonishing detail. Every trilobite track, every delicate coral branch, every discarded shell was a sentence in earth.
Farther from shore, where the light dimmed, the mood changed. The water grew colder and the color shifted from blue to green to gray.
Fewer plants lived here, but the space was not empty. Jellyfish drifted through the twilight, translucent and ancient.
Their bells pulsing silently as they hunted small plankton.
Nautiloids glided past like silent torpedoes, their shells coiled or conical, their tentacles exploring the currents.
Some were small enough to hold in your hand, others large enough to rival a human in length.
They were the ocean's first great wanderers, able to propel themselves with bursts of jet-like motion.
And then from time to time, everything changed in an instant. Storms rolled across the surface, their winds lashing the waves into chaos.
The upper layers of the ocean turned to froth, and the pressure of those storms could be felt far below, where fragile shells were tossed and buried by collapsing currents.
When the storm passed, it left behind a reshuffled landscape. Reefs broken apart, sandbars shifted. The animals that survived would recolonize the wreckage, starting again as they always had. For them, destruction and renewal were simply parts of the same cycle.
The Ordovician atmosphere was different from ours, thinner in oxygen but rich in carbon dioxide. This made the climate warm and humid, and the oceans often teemed with nutrients washed from the eroding continents.
In coastal shallows, these nutrients fueled blooms of microscopic algae, dense green clouds that turned the water opaque.
These blooms were both gift and threat. They provided food for plankton-eating creatures,
But they also consumed oxygen, sometimes creating suffocating zones where nothing larger could survive. It was in this delicate balance between abundance and scarcity that life diversified most rapidly.
The Orvish marine ecosystem became layered and interconnected in ways that had never existed before. Small crustaceans resembling modern-day krill, but from the Cambrian period, grazed on algae. Large, sensing vibrations from above. Corals grew into mounds that sheltered sponges and mollusks. Each creature relied on others, forming webs of energy that reached from sunlight to seafloor.
For the first time in Earth's history, ecosystems resemble the intricate communities we recognize today.
If you were to follow one of those currents across the world, you'd see how varied the ocean could be. In the tropics, warm, shallow waters hosted reefs so dense with life that their surfaces shimmered like underwater forests.
But near the poles, the water turned cold and clear, and life had to adapt to scarcity.
The organisms there were fewer, but often larger and hardier, built to endure long stretches of stillness between feeding opportunities.
Even then, the world was already divided into biomes: tropical, temperate, polar.
The still zones of the Ordovician Sea were like underwater deserts. They might appear empty, but their emptiness had purpose.
These were the basins where organic matter accumulated and was slowly buried.
Over millions of years, that burial stored carbon, gradually lowering greenhouse gases in the atmosphere.
The process was invisible, but it would eventually trigger one of the planet's first great ice ages.
The quietest places on Earth were, without knowing it, changing its climate forever.
In shallower regions, the story was one of noise and motion. Delicate feather star crinoids swayed in the currents. Briochuans, small colonial animals, built lace-like structures that waved gently with the flow. A primitive crown-of-thorns starfish moves across the seafloor in time-lapse, using its arms to pry open a brachiopod shell to feed. Even in calm weather, the movement of the tides stirred the sediment, carrying bits of organic material into the mouths and filters of countless small creatures. Every particle of matter was recycled again and again, passed from one organism to another in an unbroken chain.
Predation became one of the driving forces of evolution. The Ordovician saw the rise of the first true hunters, creatures that could seek out prey rather than waiting for it to drift by.
Nautiloids used their tentacles to grasp trilobites and small mollusks, cracking them open with sharp beaks. Trilobites in turn developed spines and thicker exoskeletons as defense. This slow arms race created diversity, pushing evolution toward complexity. The peaceful image of a still ocean concealed a constant struggle, quiet but relentless. When night fell, the water changed character again. Sunlight faded, and in the darkness, faint lights began to glow. Bioluminescent organisms filled the sea with pinpoints of color. It wasn't the kind of brightness that illuminated, but a gentle sparkle.
Most of these lights came from chemical reactions within small plankton, used for defense or attraction.
In the vast darkness, light became language.
If we could somehow listen to that world, it would not be silent. Sound travels far underwater. There was no bird song or insect hum, but there was rhythm. The sea itself was the instrument, and life learned to move to its beat.
Over millions of years, the geography of these oceans changed. Continents drifted closer together, closing old basins and creating new ones.
Where land masses collided, mountain ranges rose, altering weather patterns.
When they separated again, shallow seas flooded the edges of continents, forming broad shelves that became nurseries for life.
Each new configuration of land and sea created opportunities for adaptation. Evolution had endless room to experiment.
Fossils from this period show evidence of stability, punctuated by disruption.
In some places, entire reefs were buried, their coral still in place, as if frozen mid-growth.
One of the most striking features of the Ordovician was the clarity of its waters.
This light sustained vast mats of algae that carpeted the seafloor.
In some areas, these mats trapped sediments and created layered structures called stromatolites,
Living carpets that were both ancient and newly reborn. They had existed since long before the Ordovician. Every so often, volcanic activity reshaped entire coastlines. Underwater eruptions released minerals and heat,
creating local ecosystems that thrived on chemical energy rather than sunlight.
As the Ordovician progressed,
the interaction between biology and geology deepened.
The spread of marine organisms that built shells and skeletons began to draw calcium carbonate out of the water, locking it into solid form. This gradual process not only shaped the ocean floor, but also influenced the atmosphere.
Every shell that fell to the seafloor was a tiny act of planetary engineering.
In the shallows, coral reefs grew like living fortresses. They slowed waves, captured sediment, and created microhabitats for countless smaller species. Even dead reefs became new foundations for living ones.
Meanwhile, the deeper seas continued to evolve their own complexity. Organisms adapted to pressure and darkness developed unique forms.
As oxygen levels in the water rose, animals could grow larger. Energy use became more efficient. The result was a gradual shift in scale, from tiny, simple organisms to larger, more active ones.
The appearance of big predators like the orthoconies transformed the balance of the ecosystem.
Their presence forced prey species to evolve new defenses, creating an evolutionary feedback loop that fueled diversity.
And yet, in all this expansion, the rhythm of the ocean remained steady. The tides continued their daily dance. The moon, already ancient even then, pulled at the waters as it does today.
Each rise and fall of the tide left behind shallow pools where life could become stranded, forcing small creatures to... In those moments, the boundary between ocean and land grew thin. Life was still bound to the water.
Existence beyond the tide. If we could watch it unfold in real time, it would seem impossibly slow.
But over millions of years, patterns emerged. The shells became stronger, the predators faster, the reefs more complex. Storms reshaped coastlines, but life always returned. The stillness of the sea was never permanent, and the storms were never entirely destructive.
Together they sculpt a world in balance. A world ready for the next leap forward.
And somewhere beneath those waves in the quiet after a storm, a patch of algae clung to wet rock just above the tide line. Its filaments shimmered faintly in the air, exposed for the first time to sunlight unfiltered by water. The tide would come back soon enough. But for that brief interval, something entirely new was happening.
The ocean, vast and ancient, was beginning to share its gift.
The story of the Ordovich world is in many ways the story of construction. Not the kind that raises cities or bridges,
but the quiet, patient architecture of living things learning how to build.
Before this time, most creatures were soft-bodied, their forms vanishing quickly after death, leaving little trace of their existence.
But during the evolution, something extraordinary began to happen. Life discovered the power of structure.
Tiny organisms started to pull minerals from the water, shaping them into shells, skeletons, and reefs.
In doing so, they changed not only their own future, but the chemistry and texture of the entire planet. It began at the smallest scale, invisible to the naked eye. The seas of the Ordovician were full of calcium.
For millions of years, these minerals had remained mostly unclaimed. But slowly, some microorganisms developed the ability to use them, binding the minerals into hard material. At first, this was just a thin coating, a simple layer of protection against being eaten or crushed.
But the innovation caught on. Nature rarely forgets a good idea, and once the secret of
one by one, creatures began to arm themselves. Small plankton developed delicate exoskeletons. Worms and early mollusks encased their soft bodies in protective shells. Corals began secreting hard skeletons beneath their soft tissues. The ocean was becoming a world of architecture, a place where life no longer simply drifted. It constructed.
These shells were more than armor. They were survival strategies, tools that allowed animals to explore new environments.
Predators, in turn, adapted to crack or pierce these new defenses, evolving stronger jaws and more efficient ways to hunt.
The result was an evolutionary arms race that reshaped marine ecosystems.
Among the most successful architects were the brachiopods. They looked a little like modern clams, but were unrelated.
Inside, a feathery feeding structure filtered water for food particles.
Brachioids of the Rhynchellida order settled across the seafloor in enormous numbers, forming mats of living shells that covered vast areas.
When they died, their shells piled up, forming limestone beds that still exist today.
Trilobites, the old veterans of the Cambrian seas, also benefited from this new architectural revolution.
Their exoskeletons became thicker and more ornate, divided into segments that provided both flexibility and defense.
Some evolved spines, others flattened bodies for burrowing. They were not builders in the coral sense,
but their presence shaped the seafloor all the same. As they burrowed and fed, they churned the sediment,
mixing oxygen into it and creating new habitats for smaller organisms. In a way, trilobites were the gardeners of the ocean floor. Then came the corals. In the Cambrian, they had existed only as solitary individuals. Now they began to form colonies.
An intimate view of individual coral polyps connected by a single living tissue layer. They joined forces to share resources and for protection.
Each coral polyp built a cup of calcium carbonate around itself and connected with its neighbors.
Over time, these colonies grew into complex branching structures that could withstand waves and currents. Layer upon layer, generation after generation, the corals built upward and outward, forming the first true reefs in Earth's history.
These reefs were not as colorful as the ones we know today, but they were no less alive.
They provided shelter for countless small creatures, sponges, worms, chinoids, and mollusks.
Some clung to the outer surfaces, filtering water for food. Others hid in the crevices, safe from predators.
The reefs became cities, complete with neighborhoods, corridors, and hidden chambers.
Each colony was a collaboration between thousands of individuals, building something far larger than themselves without ever knowing it.
The chemistry of the ocean changed in response. As more creatures drew calcium carbonate from the water,
the concentration of those minerals dropped. This shift affected not only marine life, but also the atmosphere.
When calcium carbonate forms, it locks away carbon dioxide, one of the main greenhouse gases.
In other words, the rise of shells and skeletons began to cool the planet.
Life was altering climate through construction. The architects of shell and stone were also engineers of temperature,
reshaping the Earth's environment molecule by molecule. The consequences were profound.
Over millions of years, global temperatures began to decline. The once uniformly warm world developed cooler regions.
Ice started to appear on southern continents, setting the stage for the first major glaciation in Earth's history. None of the creatures in the ocean could have known what they were causing. Yet, their collective efforts were changing everything.
Every shell that sank to the seafloor was a carbon sink. Every reef, a climate regulator. Evolution and geology were no longer separate stories. They had merged into one.
As reefs grew, so did the diversity of life around them. Different parts of the reef supported different communities.
Deeper within, the water was calmer, home to delicate species that relied on filtered light and gentle flow.
Sponges played an important role in the system. They filtered vast amounts of water, capturing microscopic food while purifying the environment. Above the reefs, floating life continued its quiet revolution. Tiny plankton, including copepods, when they died, their bodies rained down like snow, forming thick layers of ooze that would one day harden into chalk and limestone.
This steady accumulation built the raw material for future mountains. What began
The Ordovician Ocean, for all its alien beauty, was starting to look structurally familiar. Layers of producers, consumers, and decomposers formed stable systems. Even death was part of construction. Skeletons became substrate for new life. Shells turned in. If you could compress millions of years into minutes and watch the seafloor evolve, it would look like a living city in constant renovation.
The materials of this construction were surprisingly elegant. Calcium carbonate, the main ingredient in most shells.
The diversity of building styles mirrored the diversity of the builders.
Over time, these materials would harden into rock, preserving the details of ancient lives. These fossils are the blueprints of early architecture, showing how life turned chemistry into form.
In some regions, entire platforms of limestone several kilometers thick were built by the accumulation of these materials.
Eventually, tectonic movement would lift those layers above sea level, turning ancient reefs into mountain ranges. What was once underwater cityscape became landscape. The builders of the sea ended up designing the continents.
The most fascinating part of this transformation is how unconscious it was. No organism intended to build mountains. It's a reminder of how small actions, multiplied over time, can alter a planet.
The innovation of hard parts also changed the course of evolution in subtler ways.
Some creatures developed spirals, others coils, still others layered shells that grew outward like petals.
And yet, even amid all this creativity, the ocean remained a dangerous place. Every advantage came with a cost.
Some species that couldn't afford the cost found other strategies: speed, camouflage, or chemical defenses. In shallow lagoons where sunlight shimmered through clear water, you could have seen entire communities of these architects at work. The stillness of those places was deceptive because change was constant. Reefs expanded until they...
The process was both chaotic and organized, destruction feeding creation. Life had discovered not reorganizationally.
If we could stand on one of those reefs, we'd see that even the smallest crevice held activity.
Time in the Ordovician was measured not by clocks or calendars, but by tides and sediment.
By the slow growth of coral and the steady fall of shells. The architects of shell and stone built more than protection. They built permanence.
When you walk on certain cliffs or hold a piece of fossilized coral in your hand, you're touching their legacy.
And somewhere, while all of this construction unfolded beneath the waves, the land waited. The partnership between land and sea was deepening. The ocean was busy creating architects, but the land was quietly preparing its first tenants.
The moment when life would follow the minerals home, rising slowly from salt water to sunlight.
The oceans of the Ordovician world were never still for long. Beneath the reefs and drifting plankton, the planet itself was in motion. The continents, enormous slabs of crust floating on molten rock, were slowly sliding across the globe. To the creatures of the time, these movements were invisible. No trilobite could have sensed that the ground beneath it was shifting.
Yet the slow dance of the continents was shaping everything above them. The currents, the climate, the chemistry.
The arrangement of the continents during the Ordovician looked nothing like our modern world. What we now call North America was then a tropical island continent known as Laurentia, ringed by warm.
To its east lay Baltica, a smaller continent that would one day form parts of Europe.
Farther south, an enormous landmass called Gondwana dominated the planet, extending from the equator down to the South Pole. It contained what would become Africa, South America, Antarctica, India, and Australia. Where plates moved apart, new ocean floor formed. Where they collided, one plate slid beneath another, creating the slow collision of Laurentia Baltica, and several smaller island chains during the Ordovician was particularly important. Their convergence began to close the Apatis Ocean, creating subduction zones where the ocean floor sank into the mantle. Volcanic arcs rose along the edges of the continents, forming chains of islands and mountains that would eventually become parts of. Every movement of the plates had consequences for the oceans above. When continents shifted position, they changed.
A reef that once flourished in warm, stable water could suddenly find itself in cooler, nutrient-rich conditions. The rising and falling of sea levels added another layer of complexity. The Ordovician was a time of high seas. In some regions, these fluctuations left behind alternating layers of limestone and shale.
Each limestone bed represented a time of high sea level and abundant carbonate production, when warm, clear water allowed reefs to flourish.
Each shale layer marked a retreat when sediment from the land washed in as sea levels dropped.
Together, these layers form a record of the rhythmic rise and fall of the Ordovician seas.
That pulse was more than geological rhythm. It was biological tempo. The creatures of the time evolved to match it.
This connection between plate movement and life extended beyond the seas themselves. The collisions of continents created new mountains,
which in turn began to weather under wind and rain. That weathering released minerals into rivers.
And those rivers carried nutrients to the ocean, fertilizing plankton blooms. The more the land eroded, the more. The cooling trend that began in the late Ordovician was tied to these very processes. As the continents drifted south, in this way, the Earth itself acted almost like a living organism. Its crust flexed and flowed. Its oceans breathed in and out.
To the inhabitants of the Ordovician Sea, of course, none of this would have been apparent. A well-preserved
Even so, those movements were its destiny. Its descendants' fossils would be lifted high into the air, stranded far from the sea.
When we look at the rocks from that time, we see evidence of these movements written in the smallest details. Fossilized shells tilted at odd angles.
Ancient coral beds folded into arches. Seams of volcanic ash interwoven with limestone.
One of the most dramatic consequences of plate motion was the creation of new habitats. As continents drifted apart, they forming isolated basins. These basins became evolutionary laboratories where species could diverge and adapt to unique conditions. Over time, the interactions between these geological and biological systems created feedback loops that stabilized the planet. The evidence of these cycles is preserved even in the fossils themselves. The chemical composition of shells reveals changes in ocean temperature. It's easy to think of continents as immovable and oceans as eternal. But the order of reminds us how transient they are.
To the Earth, 1,000,000 years is a heartbeat.
By the end of the Ordovician, the continents were drawing closer together. The global temperature had dropped, and glaciers were expanding. Sea levels began to fall, exposing once submerged reefs and coastlines. For the creatures of the shallows, this was a slow disaster.
The tectonic collisions that built mountains would feed rivers that nourished oceans.
The story of the Ordovician did not end with stillness or collapse. It ended with transformation.
The planet setting the stage for another leap forward, another wave of creativity, another chapter in the long experiment of life.
The sea's pulse slowed, the air grew colder, and the surface of the world began to change.
The architects of shell and stone had done their work well. The planet they had built was strong enough to endure its own heartbeat.
And as the water cooled and the continents settled into new positions, the next part of the story was already beginning.
The Earth was cooling, the continents shifting, and the reefs of the order world rising and falling with the tides of time.
Yet for all the grandeur of continents colliding and oceans breathing, the real transformation was taking place on a smaller scale.
It was the tiny, drifting, multiplying multitude of small things. The plankton, the algae.
Collectively, they orchestrated the chemistry of the planet. turning sunlight into sustenance, carbon into stone, and chaos into order.
If the great reefs were the monuments of the Ordovician, these tiny beings were its engineers.
The ocean was their stage, and the performance they gave was endless. A symphony conducted by sunlight, temperature, and time.
It began near the surface, in the thin band of light where the sun's rays could still reach.
Here, microscopic organisms floated and drifted, capturing photons and turning them into chemical energy. Cyanobacteria, descendants of even older lineages, continued their ancient work of photosynthesis, releasing oxygen as a byproduct.
Alongside them, thrived new groups: green algae, red algae, and the first eukaryotic plankton. Their diversity exploded during the Ordovician, and with that explosion came stability. The ocean was learning to breathe deeply and evenly, the balance of gases and nutrients smoothing into rhythm. Every morning as sunlight warmed the surface, diatoms, a type of plankton, rose toward it.
This vertical migration created a pump that slowly moved carbon from the surface to the deep sea. It was indigenous. The planet's first biological carbon pump was in motion, transforming climate regulation from a purely geological process.
The consequences were immense. Over millions of years, this slow, steady export of carbon lowered greenhouse gas.
One of the paradoxes of Earth's story. The smallest organisms created the conditions that nearly extinguished much of life. Yet without their quiet industry, the air would never have become breathable, nor the world ready for the expansion of complex life to come.
Beneath the surface, the products of their labor fell like snow. When plankton died, their shells and bodies drifted downward,
collecting on the seafloor as fine sediment. Over time, this rain of microscopic debris formed layers of...
Even now, entire landscapes, white cliffs, pale hills, rolling plains, are built from the remains of these small things.
Among them were the graptolites, colonial planktonic animals that floated in the open ocean.
Each colony consisted of many small individuals housed in a shared structure, a kind of organic skeleton.
Today, paleontologists use graptites to date Ordovician rocks with precision. They were nature's timekeepers.
Their remains scattered like notches along the planet's geological clock.
Closer to shore, another microscopic world thrived on sunlight and minerals washed from the continents. Datum-like algae and other early phytoplankton formed thick blooms that colored the water green. These blooms were not just biological phenomena. They were engines of transformation.
As they multiplied, they consumed nutrients, altered oxygen levels, and sometimes triggered cascades of chemical change that rippled through entire ecosystems. When the blooms collapsed, the decay of so much organic matter could deplete oxygen,
creating anoxic zones where few large organisms could survive. The balance between productivity and suffocation was delicate, but over millions of years, it drove evolution to new levels of resilience. In the quiet shallows, microbial mats still held on, relics of a more ancient Earth. Layered communities of bacteria and algae formed films over rocks and sediment, trapping grains of sand and building structures called stromatolites.
They were the foundation beneath the reefs, silent and steady.
What makes these tiny organisms remarkable is not just their abundance, but their cooperation.
Algae produced oxygen that bacteria used to decompose waste. The decomposers in turn released nutrients that fed the algae.
The entire system was built on exchange. The larger animals of the Ordovician, trilobites, brachiopods,
plankton fed the filter feeders, which in turn fed the predators. When plankton populations rose, the entire food chain prospered.
The reefs might have seemed like the center of life, but in truth, the ocean stability came from the surface.
If you could follow a single particle of carbon through this world,
you'd see it move through many lives. It might begin in a ray of sunlight captured by a Spirogyra algal cell. Then it could pass into sediment as waste, then into a bacterial cell, and finally back into the water as dissolved gas.
This efficiency made the Ordish Ocean extraordinarily productive. Fossil evidence suggests that
the expansion of plankton and algae transformed the marine biosphere into a complex, self-sustaining system.
It was no longer a collection of isolated species, but a network of interactions stretching from surface to seafloor. But this new system also introduced vulnerability. The same processes that made the world stable.
When the balance between carbon burial and release shifted, global climate followed. When nutrient flows increased too much, oxygen levels dropped. The symphony of small things could shift from harmony to dissonance without warning.
Yet for the most part, the Ordovician Ocean thrived. The regular cycles of light and dark, warm and cool.
The air above was changing too. The oxygen released by marine photosynthesis began to accumulate in greater.
This shift altered the chemistry of the atmosphere, allowing ozone to form in the upper layers. That ozone shielded the surface from ultraviolet radiation,
making it safer for life to eventually venture onto land. The small things, without intent or awareness.
The ocean's stability came from the surface. In some parts of the world, particularly near the equator, the planet was no longer a uniform sphere of water and rock. It was beginning to show character, pattern, and diversity.
When we look at Ordovician rocks today, we can still see the fingerprints of these tiny organisms.
The truth is that the world has always been run by the small. Even now, the majority of Earth's oxygen comes from plankton in the sea.
The symphony has never stopped playing. It has simply changed its key. The interactions between small and large life forms also changed the physics of the ocean itself.
More organic matter sinking meant more oxygen consumed in the deep sea, leading to the creation of layered oceans, oxygen-rich above, oxygen-poor below.
Over time, this layering helped create the first stable deep ocean ecosystems. Bacteria that could survive
in this balance of light and dark, of photosynthesis above and decomposition below, the planet reached a new kind of equilibrium.
The symphony of small things was in truth the orchestra of stability.
When the great ice sheets began to spread across Gondwana toward the end of the Ordovician, much of it was a consequence of this very stability.
The small things had drawn down enough carbon to cool the world. They had without intention composed the overture to the first great mass extinction.
Yet, even as ice advanced and seas retreated, the system endured. Some plankton adapted to colder water. The oceans of the Ordovician might seem distant and alien, but they were the testing ground for every ecological. And as their work continued, as the light filtered through the upper waters, something else was beginning near the shorelines. Algae that had once lived entirely submerged were starting to linger a little longer above the waterline, their cells adapting to brief exposure to air. The Ordovician Ocean was full of movement, but not all of it was gentle. For hundreds of millions of years, life had been soft and slow.
Now, something different was emerging. Predators were becoming more efficient.
Predation had existed since the dawn of multicellular life. But during the Ordovician, it took on a new scale.
Creatures developed stronger limbs, sharper appendages, better senses, and more coordinated behaviors.
Among the most visible of these new hunters were the nautiloids. They were cephalopods, distant ancestors of squids and octopuses, enclosed in shells that could be straight, curved, or coiled. Some were small enough to fit in a hand, others stretched several meters in length.
They moved through the water by jet propulsion, drawing water into a chamber and expelling it through a funnel-like siphon.
They could hover, drift, or dart forward in bursts, controlling direction with fine adjustments of their tentacles and shell orientation. At the front of each knout was a ring of tentacles surrounding a beak-like mouth. They hunted trilobites, small mollusks. When they struck, they used both force and suction, pulling victims toward the beak and breaking through shell or exoskeleton with crushing power. The presence of such predators changed everything. Creatures that had once lived openly on the seabed began to hide. Trilobites burrowed more deeply or evolved spines for protection. Brachiopods anchored themselves in tighter crevices.
Even simple worms began to dig deeper tunnels, carving networks through the sediment that served as refuge from the hunters above.
Evolution was no longer just about growth and reproduction. It was about defense and awareness.
For the smaller creatures of the reefs, survival depended on quick reactions. Starfish, then still relatively new,
They moved slowly, but their ability to pry open shells and feed on soft tissue made them dangerous to stationary prey. Crinoids, the so-called coelies, responded by growing taller, lifting their delicate feeding arms farther from the reach of ground-dwelling predators.
In this way, the vertical dimension of the ocean became more important. Life was spreading not just outward, but
The complexity of these microhabitats fostered specialization. Each species found a particular niche, a depth.
Diversity multiplied not because of stability, but because of competition. The arms of the ocean reached everywhere, and everything had to adapt to their touch.
At the same time, predation led to the evolution of sensory systems. Animals began to respond not just to touch or light,
but to chemical signals in the water. The faint trail of a wounded animal, the subtle vibrations of movement,
all became part of the sensory landscape. This invisible web of signals made the order of Vision Ocean alive in new ways. For the nautiloids and other active hunters, this meant a form of awareness, not intelligence as we understand it, but a growing sensitivity to the environment.
For prey, it meant vigilance. For predators, it meant strategy. The dynamic between them,
awareness driving adaptation, adaptation driving complexity.
The arms of the ocean were not only tentacles and limbs, but also the metaphorical reach of evolution itself.
When burrowing became common, oxygen levels in the sediment increased, allowing new species of bacteria to flourish. Fossils from this time record evidence of these struggles. Some trilobite shells show healed bite marks. Scars from attacks survived.
But it was a beautiful battlefield. Predation, though destructive, brought balance and innovation. It prevented dominance by any single group and encouraged diversification. In a sense, predation was the engine of creativity.
Some of the most curious creatures of this era were neither pure predators nor pure prey, but opportunists, scavengers, and filter feeders.
The balance extended beyond biology and chemistry. Predation and scavenging stirred up sediments, releasing nutrients that fed plankton blooms.
It was a closed loop. Destruction feeding creation. Hunger maintaining balance.
The rise of predators also changed the tempo of reproduction. Species with shorter lifespans or higher fecundity.
Still, the predators of this time were not the apex hunters we imagine today. They lacked the speed and intelligence of later fish.
But they were pioneers. Their presence rewrote the rules of the ocean. Before them, life had been content.
In the shallower zones, where sunlight penetrated and reefs thrived, this evolutionary contest was particularly.
Some had eyes designed for the shifting light of shallow water, others for the dim glow of the deep. Their vision was among the most advanced of its time. In deeper water, where light faded to green and then to black, the arms of the ocean took on other forms.
There, soft-bodied predators relied on touch and chemical detection rather than sight. They moved through the darkness like living senses.
Above the reefs, nautiloids drifted like sentinels. Their shells, filled with gas chambers for buoyancy, allowed them to hover effortlessly.
all of this movement and interaction created a form of stability through complexity. When ecosystems become
As the period progressed, the predators grew larger and more specialized. The top of the food web became crowded with competition. But even this flourishing carried the seed of change. The cooling climate, the shifting continents, and as glaciers advanced across Gondwana, sea levels would begin to drop, compressing habitats and driving new pressures.
Yet for now, the seas remained full, the predators restless, the reefs alive.
Soon those arms would reach even farther, not just through the water, but toward the edges of the sea, where the first algae.
The reefs of the Ordovician seas had been growing for millions of years, each one a slow and steady masterpiece.
They were not coral reefs in the modern sense, not the brightly colored structures filled with tropical fish that we might imagine today. But their function was the same. They were the backbone of biodiversity, the architecture of life beneath the waves.
If you could have drifted over one of these ancient structures, you would have seen a landscape of extraordinary variety.
Mounds and ridges of coral, sponges, and algae rose from the seafloor like underwater hills.
Corals, though small and individually fragile, were powerful in their collective effort. Each one built a cup of calcium carbonate around itself, anchoring to rock or to the skeletons of earlier generations. As they died, their remains became the foundation for new colonies. Alongside the corals were stromatoporoids, sponge-like organisms that also built rigid skeletons. Their smooth surface, the reefs became homes for a multitude of other beings. Crinoids anchored themselves to the coral skeletons, spreading their arms to catch drifting food.
Small Devonian pleurotomariid mollusks grazed on algae that grew in patches of sunlight. Phacops trilobites.
For millions of years, these coral cities expanded. They followed coastlines, spread across continental shelves. Behind these natural walls, calmer lagoons formed, rich in plankton and fine sediment. These sheltered areas became nurseries for young animals.
The diversity within these ecosystems was astonishing. In some fossilized reefs, paleontologists have. The chemistry of the reefs also shaped the ocean around them. The corals extracted calcium carbonate from.
If you could touch the surface of one of these reefs, you'd feel that it was alive but solid, both fragile and enduring. The living layer was thin, perhaps only a few centime deep, but beneath it lay meters of compacted skeleton. And yet, for all their strength, the reefs were vulnerable. They depended on clear, sunlit water and stable conditions.
But as soon as the water cleared, new colonies began to grow. Life was persistent. It used every opportunity to rebuild.
The balance between construction and erosion was delicate. Wave action constantly wore away at the reef's surface, breaking pieces free.
Those fragments settled nearby, forming new mounds that could become the foundation for future growth. In this way,
Symbiotic partnerships like those between corals and algae had begun to emerge. The algae lived in
exchange for protection and nutrients. This cooperation allowed corals to grow faster and build stronger skeletons.
For the smaller residents of the reef, the structure offered both opportunity and risk. Shelter was abundant, but so were predators.
Fossil evidence suggests that some reefs are home to thousands of individuals per square meter. The density of life was extraordinary.
The stability of these systems gave life the chance to refine itself. With reliable food sources and protected environments,
For a long stretch of the Ordovician, these coral cities and quiet kingdoms represented one of the most successful experiments in Earth's history. And then slowly the balance began to shift. The continents moved, climates cooled, and sea levels fell. The reefs that had flourished in warm, shallow seas found themselves exposed to air or submerged in colder, darker water.
The quiet kingdoms began to empty, the coral cities to crumble.
but even as they declined, their legacy endured. The reefs left behind thick layers of limestone.
For hundreds of millions of years, life had known only the sea. Every breath, every movement, But near the end of the Ordovician, something subtle began to change. The boundaries of water, once absolute, were beginning to blur. The process was not dramatic. It began instead with something simple, almost unnoticeable. Algae spreading across wet rock.
Over time, some began to tolerate brief exposure to air. When the tide retreated, or waves...
The land itself at this time was barren. There were no plants, no soil, no insects. The continents were mostly rock and sand.
Yet along those coastlines, the first stains of green began to appear. Thin films of algae.
It's difficult to overstate what this moment represented. For billions of years, water had been life's only refuge. To leave it even briefly meant confronting an entirely new set of challenges: desiccation, temperature swings, ultraviolet radiation, gravity.
But those that survived the longest began to develop simple adaptations: thicker cell walls, mucus coatings.
While algae were the pioneers, other forms of microbial life followed. Cyanobacteria spread into damp environments along riverbanks and tidal flats. They formed biofilms that stabilized sediment, reducing erosion and helping retain water. These films acted as the first primitive soils.
This slow colonization of the shoreline had enormous implications. By binding sediments and retaining moisture.
Back in the ocean, these changes were felt too. Rivers began carrying slightly different loads of minerals into.
At the same time, some aquatic plants began to develop more complex reproductive strategies. Many algae released spores or gametes into the water.
But in the unstable environment of the shore, this approach was risky. Over time,
This innovation, though simple, was crucial. It was the first step toward the idea of the seed, the continents. As land and sea grew more intertwined, the climate continued to shift. The drawdown of carbon dioxide had cooled. The shallow seas that had once covered vast regions began to retreat. In many areas, the exposed seafloor became tidal flats.
in these flats, thin crusts of microbial life took hold, stabilizing the surface.
Some animals, like certain burrowing worms and aeropods, learn to tolerate short periods of exposure to air.
It's important to understand that evolution does not plan ahead. The algae on the rocks and the bloodworms in the mud.
Yet, looking back, it's impossible not to see purpose in it. The slow, inevitable unfolding of potential.
The sunlight that struck those ancient coastlines was the same sunlight that falls on modern shores. But to the organisms of the
As oxygen levels in the atmosphere rose, conditions on land became more favorable. Ozone formed in the upper layers.
The appearance of life on land also altered the physical landscape. Algal mats and microbial crusts began to. They trapped dust and spores, creating patches of organic rich material. Over time, these patches grew deeper.
The continents, once inert, were beginning to breathe.
It would be millions of years before true plants appeared with roots and stems capable of supporting themselves on dry land.
The step toward the sun had begun. In many ways, this transition reflected the broader pattern of the first green on land was not a revolution. It was a whisper. Yet that whisper would eventually change the color of the earth itself.
The earth had been restless for so long. Continents drifted, oceans opened and closed.
Yet by the middle and later stages of the Ordovician, the planet was beginning to settle into a new kind of rhythm. Not stillness, but regularity.
The forces that shaped this rhythm were both geological and biological, inseparable in their influence.
The Earth's carbon cycle was central to this newfound stability. Carbon dioxide entered the atmosphere through
But during the Ordovician, life began to take control of the process. Plankton and algae absorbed carbon during photosynthesis. The result was a slow, natural removal of greenhouse gases, a planetary thermostat managed by living things.
The ocean was where this rhythm was most visible. Every day, light and darkness governed them.
Above the ocean, the air was changing too. The rise in oxygen levels created an atmosphere that would have been breathable for modern animals.
As the planet cooled, another kind of rhythm emerged, the glacial cycle. Ice began to accumulate.
This idea of dynamic stability is one of the most profound lessons from the Ordovician world.
The Ordovician has often been called a second explosion of biodiversity, following the Cambrian species multiplied in every habitat. To imagine the Ordovician world in motion is to picture a system that never truly paused. Yet stability is never permanent. As the period progressed, the same forces that had created balance began to push it toward a new state. The ongoing drawdown of carbon dioxide cooled the planet further. While the growth of glaciers lowered sea levels more dramatically than before, the rhythm of the planet was steady, but its tempo was slowing. The warm intervals grew shorter, the cold ones longer. By the end of the Ordovician, the Earth would experience one of the first great mass extinctions, a consequence not of sudden catastrophe. For millions of years, the Ordovician world had been thriving. The reef stretched wide across the shallow seas. But that balance, like all things on this planet, was not meant to last. Without warning, the rhythm began to falter. The beginning of the end came softly. The air grew cooler, and the glaciers that had been confined to the southern... As ice grew, it locked away enormous amounts of water. Global sea levels fell, perhaps by more than 100 meters. The shallow seas that had covered much of the continents, the nurseries of Ordovician life, began to retreat.
Reefs that had flourished for millions of years were left exposed to air. Coastlines shrank, habitats vanished. The creatures that depended on warm, sunlit shallows were the first to suffer. Corals, strumataperoids, and the ocean, once vibrant and noisy, grew quiet.
In the deeper seas, the effects were different but equally severe. As the cold spread, the chemistry of the ocean changed.
Entire ecosystems collapsed, not from direct destruction, but from deprivation. A slow starvation that spread through the food chain. Ordovician extinction unfolded in two main waves, separated by a brief and deceptive pause. The first came with the onset of glaciation. Then, after millions of years, the ice began to melt. Sea levels rose again, flooding the continents once more. The sudden influx of cold, oxygen-rich water from melting glaciers disturbed the deep ocean, releasing nutrients and triggering blooms of plankton.
These blooms consumed oxygen as they decayed, suffocating marine life in vast regions of Anoxia. The second wave of extinction followed.
By the time it ended, perhaps 80% of marine species were gone. The trilobites, so dominant.
And yet, even in its devastation, the extinction was not uniform. Some regions suffered more than others.
A few hardy brachiopods survived in colder waters, adapted to low oxygen and limited food.
If you could have stood on the shores of that frozen world, you might not have recognized it as the same planet that had glowed with tropical warmth.
The quiet was perhaps the most striking thing. The Ordovician had been filled with the constant hum of life. Now much of that had ceased. The sediment settled undisturbed. The reefs crumbled. The planet seemed to pause.
This silence was not permanent. Life has never been still for long. The survivors of this age...
The extinction also reshaped the planet's chemistry. As glaciers scraped across the continents, they exposed fresh rock to weathering.
When the ice melted, rivers carried vast amounts of minerals into the sea, fertilizing it anew.
The ecosystems that emerged were not the same as those that had vanished. Coral types changed. New species of plankton evolved.
The quiet catastrophe was not a failure of life, but a reminder of its dependence on the planet's rhythms.
When scientists study the rocks from this time, they see evidence of both destruction and renewal. Layers of glacial deposits mark the advance of ice.
Black shells record the oxygen-poor seas that followed. Fossil assemblages show abrupt breast.
Yet above those barren layers, new fossils appear, marking the beginning of recovery. The pastorers. The extinction's legacy reaches far beyond its moment in time. By removing dominant species and clearing ecological...
The survivors diversified in the Silurian, creating new reefs, new food webs, new strategies for life.
It's easy to imagine extinction as sudden, dramatic, or violent, but the Ordovician event was mostly slow, quiet, and inexorable. There was no single explosion, no comet, no instant destruction. The world simply changed.
And yet, within that fading, evolution never stopped working.
in the cold, isolated pockets where... In the aftermath, as the glaciers began to melt and the seas returned, the Earth entered a new chapter. New communities began to form on the freshly exposed seafloor. The first hints of coral recovery appeared. The Ordovician extinction was one of the great tests of life, a test that would be repeated many times throughout Earth's history. It showed that even the most complex systems could fail, and that recovery was not guaranteed, but earned. If one could have watched those millions of years unfold in fast motion, the pattern would look almost peaceful.
The catastrophe had been quiet, but its lessons would echo through every age that followed. And out of that long stillness, the Earth would begin to sing again.
When the ice of the origin began to withdraw, the world revealed what it had become. The silence that had lingered over